Thank you for the invitation. I'm very happy to be here to talk about some of the exciting things that have been going on at the Galactic Center. So this year has been particularly exciting because it's a confluence of many things are happening. And so the work I'm going to talk to you about is a collaboration between many people. They're all listed here with folks from UCLA, but also from other institutions around the world. And then in bold, I've highlighted all the many graduate students who's been part of this work, and they've been really integral to getting a lot of this done. So to begin, this is a really nice video of the Galactic Center. So this is the Milky Way in optical light. And then we can zoom in into the middle where it's sort of empty in optical. And as you zoom in, then now we switch to a Spitzer view. And so here is what we mean by the Galactic Center. It's really bright and has the densest and most massive star cluster in the galaxy. And as we zoom in more, now this is HST, where the angular resolution is better. But at the very center, you really need adaptive optics in order to resolve the stars around the center. And the motions of these stars was what helped us measure the mass of the black hole, for example. And you probably have all seen that video. But I'd like to move on now to talk about what is the environment around this black hole and what are the physical processes that we can use the Galactic Center as a laboratory to study. So my abstract was, I realized after a little too ambitious. I talked about 3 different topics that I wanted to talk about at the Galactic Center. But I really only have time for 2. So the third one I'll talk about at lunch, if you like. And so we're going to do a quick poll, which 2 topics you'd like to hear about during this presentation itself. So first is the test of general relativity using the stars in orbit around the supermassive black hole. And in particular, this is the measurement of the gravitational redshift from the star SO2 as it passed by the black hole in 2018. The second is what is the nature of the near-infrared emission from Sagittarius stars. So the black hole has an emissive counterpart in the near-infrared, and that infrared source has been studied for many years now over 20 years. But this year, something unusual seems to be happening to this activity. So I can talk about that. Or third, I mentioned that the nuclear star cluster of Milky Way is the most massive and densest star cluster. How did it get there? How's that related to the formation of the galactic nucleus? And so what we've been trying to do is to build the first chemical dynamical model of the nuclear star cluster to help answer some of these questions. OK, so show of hands. First question, first topic. OK, topic number 2. OK. Topic number 3. Oh, God. So my poll did not work.
Focus on ground truth instead of speculation.
OK, sure. Grad students. Poll number 2. Topic 1. OK. Topic 2. OK. Topic 3. It's the same problem. OK. For the sake of moving this on, I'll talk about the first 2, and then you can ask me lots of questions about the third one and meet with me to talk about it. I'm actually super excited about this one too.
You will have time in the Macal lunch to talk about.
I think that would confuse me actually. So test of general relativity. So this is one of the big questions a lot of us are asking in astrophysics in terms of tests of gravity. Is general relativity the correct description of our supermassive black holes? It's been tested in lots of different regimes, including very well in the solar system, but not necessarily near supermassive black holes. I like this cartoon from the XACD, where this Einstein says we need to change space and time to make things work, and then the other person off screen says that's your solution to everything, which is literally true. So why do we want to do this? So 2018 is our first opportunity to test general relativity with stellar orbits around a supermassive black hole. And then this is a diagram of basically the potential versus mass. And you can see that SO2, which is the star around the supermassive black hole, occupies this interesting regime. The reason we want to test gravity around different types of objects and different gravitational fields is that we don't know where the limits of general relativity lie. And so some theories, for example, predict that there might be violations of GR around compact objects, but not around things like the Earth, for example. OK. So how are we going to do it? So in 2018, the star called SO2, which has a 16-year orbital period, went through its closest approach. And during its closest approach, we can measure the gravitational redshift that's predicted by general relativity. And here is just a video representing that. So the top plot is the line of sight velocity as a function of time. And then the bottom plot is the relativistic contribution of the line of sight velocity. And so you can see as the star goes around, basically nothing happens for a long time in terms of this relativistic thing. And then as it goes through closest approach, you see a giant spike at 200 kilometers per second. OK. So since I'm an observer, we're going to start with observations. So in order to do this, actually, you can't just observe in 2018, right? Because you need to know the Keplerian orbit model well enough that you can say it's a deviation due to general relativity or maybe some other theory of gravity. And so it really took 20 years of data in order to do this experiment. And in 2018, that was actually the second time we saw the star SO2 go through closest approach. The first time was in 2002. And that time, we didn't know the orbit actually enough to know that it even went through closest approach until after it did. And so this was basically the first time we could do this test. But one of the big problems is, right, telescope time is scarce. I would love Keck to give us, every night for the whole summer, but that's not going to happen. And so how do we optimize our observation? And there's a lot of competing factors. For example, how many observations does it take to reach a certain goal? In this case, the measurement of the redshift. What type of observations do you need? So orbits, we use two kinds of observations: positional observations and then radial velocity measurements. And then the third is really important. When do we need to take these measurements? Because certain parts of the orbit are more important than other parts of the orbit. And so as part of this, we developed an efficient optimization tool to try to figure out what's the least amount of observations you need to take to maximize some measurement. So it actually gave us some really interesting and not counterintuitive results at first. And it turns out that when we ran this tool, it told us that the most important points to measure are the radial velocity maximum and minimum, which is not necessarily surprising. The surprising part is that it doesn't actually want very many observations at closest approach itself. And so it took us a little while to understand this. And the reason is because measurements at closest approach actually is where you maximize the correlation between things like distance and mass. And so it's not as helpful to differentiate between the redshift signal. Put it another way, basically these. So if you basically tell the tool, the optimization tool, that we know the mass and distance precisely, it will tell you that you should measure it at closest approach. And so based on this this tool, that was how we designed the experiment in 2018 to basically get this turning point and this turning point. I didn't show you the astrometry, but the astrometry you do want the closest approach in astrometry. Okay, so basically this was our experiment in 2018. So we were going to observe closest approach with astrometry. This is astrometry on this plot, and this is radial velocity. And we're going to try to observe the velocity maximum in April, and then the velocity minimum in September.
Can you remind us what flavor of star this is and how accurately you can measure a radial velocity?
Oh yeah, I will go very deeply in detail with that because it turns out a lot of systematic errors creep up in exactly that question. Yeah. So For those who are not orbit aficionados, this is the geometry of the orbit of SO2. It actually has a very interesting geometry. So this is the plot you usually see, which is the plane of sky direction. So this is projected distance in x and y, but then these are the z directions. So actually, if I'm the supermassive black hole and SO2 is going around me, basically it's in 2018 it was here, and then as it went through closest approach, the orbit's actually in front of the black hole. And then after September, it went behind the black hole. So basically, if you think of the sky as a plane, the orbit intersects the plane along this black line here. So only a little tiny bit of the orbit is in front of the black hole. And you can also see why the turning points are so important, right? So that's exactly where it crosses the plane of the sky. And so that's why the orbital parameters become really well measured once you get these points. Okay. These are the telescopes we use. So these are they're 4 lasers. We need to use laser guides to our adaptive optics because we need the angular resolution, basically. And all 4 telescopes on Mauna Kea participated in this measurement in 2014. This picture, it's 2018. This picture was taken in 2014. We didn't simultaneously observe with all 4 telescopes in 2018 because that's a little bit of a waste of telescope time. Yeah, so that's just to show that. And then here we go. Next. So this is like my summer vacation slides. So this is in March was our first data radial velocity measurements in 2018. We didn't realize how lucky we were on this night, actually, because for the next 7 nights that we tried observing, so we basically observe about once every 2 or so we observe basically like 4 nights every 2 or 3 weeks, basically. But basically for the next like 10 nights, we were weathered out. Mauna Kea had historically bad weather in 2018. Something like 75% of the nights were lost in winter and spring of that year. So yeah. So finally, after a lot of bad weather, we got back on the telescope again, and here's us being happy about that. And then on May 17th, Kilauea exploded. So this was the morning right after we finished observations. And there were these webcams that look out on the mountain, and then the telescoper was like, "Hey, what's going on?" in one of these webcams, and that's what happened. It was Kilauea, which is a volcano, not the volcano where the telescopes are, but the active one exploded, and so you can see this like dust plume like explode out from underneath. So interestingly, the reason, like this volcano did impact our observation because right after this happened, there was a 6.5 earthquake that occurred. And so the telescope had to be shut down for several nights to make sure everything was fine. And when the telescope was brought up again, we found out that the laser basically broke because of the earthquake. And so it took them several more nights to fix it. So we didn't get observations for a little bit. The other thing that the volcano did was it increased the sulfur dioxide in the atmosphere. And then, when that mixes, or it increases the amount of sulfur in the atmosphere. And when that mixes with water, it can make an acid, essentially, and it could hurt the mirrors. And so whenever there was enough like fog, which is volcano fog, going over Mauna Kea, they have to close the telescope. Anyway, challenging, to say the least. So this is closest approach. Oh, by the way, I forgot to tell you who these people are. But this is Andrea Guez, of course, who's the director of the UCLA Galactic Center group. This is Mark Morris. This is Gunther Witzel, who does a lot of Saturday star work. This is Joel Chet, who is a grad student. And this is Arazu, who is also a grad student. And these are also other grad students in the group observing RV min. So the grad students got a lot of training observing in 2018, let me tell you. So they're all pros now. And then here is us observing RV minimum in September. Okay. So after we get all these data, what do we do with it? This is now getting the question about the spectroscopy. The way we fit the spectra of SO2 is we are building a physical model of the spectrum. So essentially we use a synthetic grid of spectra so that we can get things like effective temperature, surface gravity, velocity, rotational velocity, and importantly for this project, the radial velocity of the star. And the reason why we went through all this effort is, I'm going to give you a moment, but the software we use is called StarKit, and it's publicly available if anyone's interested in using it. It's pretty useful. And so here's an example of the star SO2. So SO2 is an early type B star, which means it's fairly massive. It's about 14 solar masses. And because it's massive, it's also very hot, right? So its temperature is around 35,000 Kelvin. And that means that you really only see hydrogen and helium lines in its infrared spectrum. And this is a fit of the bracket gamma line, which is a hydrogen absorption line in the spectrum. And this is in orange is the data. So this is flux as a function of wavelength. And then in blue is our model. So the model, you can see, has all these little wiggles. So this is the main hydrogen line. And this little bump here is actually a helium absorption line. So this allows us to basically map the correlation between the different parameters. And so it helps to get a more accurate rate of velocity. And this was important because we realized that our previous method had a flaw, big flaw, which is that in the previous method, we just fit a Gaussian. It seemed like that seemed to be OK in the past because this line looked fairly Gaussian. But as you get to higher and higher signal noise, you notice this helium bump becomes more and more prominent. And actually, it will bias your Gaussian measurement. And so here's an example of a very high resolution version of a B star fit with StarKit versus a Gaussian. And in order to figure this out, for about 4 years before 2018, we've been taking radial velocity standards every night that we took observations of the star, and so that we can make this plot. So this is to compare our new methodology with a previous methodology. So there's actually a fairly significant offset from using a Gaussian fit. It's about 8 kilometers per second different than if you use this more complicated physical modeling.
Why can't you fit the star spectrum against itself?
So it's a good question, and but you don't know how do you shift the spectrum to stack them? It's one question. So it's really hard to know the absolute. We need the absolute velocity. It's actually really important for this project. I'll get to why that is actually in a moment, because there's a strong correlation.
So
yeah.
You showed us the bracket gamma lines, but how many lines of comparable strength do you actually have to prove it?
So this is the strongest line in K-band. There's another helium line that's weaker, and it turns out that there's various reasons. One of which is our instrument has a specific wavelength range, and depending on the radial velocity of SO2, sometimes that line is not inside the radial velocity range of the instrument. So sometimes we have that line, sometimes we don't, but this is the strongest line that's always in there.
Most of the signals coming from bracket gamma?
Yeah, that's right.
So is most of the problem Gaussian, or the fact that you didn't include helium?
I think it's both. One of the reasons is that spectral lines are not really Gaussians because the wings are, the wings are basically has to do with the physical processes in the surface, and so that is why I think a lot of it the bias happens too. So for example, see how like this wing part is different. Yeah. And one of the things that helped actually, not only it became more accurate, we got much better precision. So we almost increased our radial velocity measurement by almost a factor of 2. And so we actually went back through all the historical SO2 data and then reduced it and re-derived radial velocities. Okay. So here is here's what the radial velocities look like. It's like this is pretty incredible for me because so basically between 2017 to July of 2018, it moved by like 4,000 kilometers. So right, like you don't often can measure radial velocities with your eye like this. So if you stack the spectrum really, basically all the spectrum, this is what you see. You see really strong helium line, hydrogen line. There's also a little tiny helium line here, which can't actually be separated in individual spectra. But the other helium line I was talking about is way over here at 2.01 something. OK, so that's the radial velocity. And now on to the astrometry, right? We also have imaging of the Galactic Center. And so here's a movie that was put together by Almat Gautam, who's one of the grad students at UCLA. And the movie is going to show you 24 years of data, like real data now, just roughly aligned to each other, so the images like are in the same spot of the stars at the Galactic Center. So here they are. You can see there's a transition at some point. So for the first 10 years or so, up to 2000, from 1995 to 2005, we used something called speckle imaging, which is diffraction limited but very low signal to noise, basically. And then in the last 14 years of data are all adaptive optics data. So you can see lots of interesting things. This movie is like mesmerizing to me all the time. But so not only is SO2 here, right? If you notice these really bright stars, so when it goes again, look at the bright stars. Like, you see how it rotates? Isn't that cool? So those are young stars at the Galactic Center, and they are all in the same orbital plane. It's wild, right? So about something like 25% of the young stars are in this orbital plane, and you can just see it from this video. Sorry?
How do you register the image?
Oh, yeah, I'm going to get into this. So the reference frame is one of the most important pieces of this whole experiment, right? Because if everything moves, how do you make a reference frame? And I'll get to that in 1 second. OK, so but first, the actual positional measurement. So the speckle data that I was showing you before is actually much higher quality than the previous time. So speckle is basically where you take images of the sky at very, very short exposures, basically shorter than the time that the atmosphere can move, basically. So you basically freeze the atmosphere. And so if you've ever seen speckle images, they're like this weird like bug splat pattern, basically, where every single piece of the pattern is about basically a diffraction limited core. And then the trick in speckle is that it's hardware cheap, software expensive, which is you have to combine these images. So you take thousands and thousands of images a night, and you have to combine them into one image somehow. And then in the past, we use a very simple algorithm which calls shift and add, which is literally take the brightest pixel, shift them all to the same spot, and then add up all the images. And this leaves only basically 5% of the light in the diffraction limited core, and most of the light actually just elsewhere. In more recent years, we've switched to a more Fourier-based mode called speckle holography, which basically just combines them with better information about exactly where all the speckles are located. And so we've achieved about a magnitude of improvement actually in sensitivity in the speckle data. And that's actually improved both the observations of SO2, but also the observations of the black hole that I'm going to talk about in a second.
How large is the asymptotic patch compared to
So at 2 microns, it's roughly like 10 arc seconds or so. It degrades really fast once you get beyond that. Yeah, so R naught, which is the parameter that adjusts that scales with wavelengths and things, is about I think 20 centimeters ish on Mauna Kea. It scales with seeing as well. Okay. So we're going to talk about better alignment. So we did a better alignment, which I'll talk about soon. There's a new optical distortion map because the AO system changed slightly. And then here in 2008, we usually use K-band observations, which is at 2 microns, where the stars are brighter because of the extinction. But that also means the black hole is brighter. The black hole is actually very red. And so in 2018, we switched to a shorter filter so that we can minimize confusion with the black hole itself, because the black hole is an emissive source. OK. And then we also looked at the impact of stellar confusion. So this is a residual from an orbit fit in X, and then in versus time, Y versus time. You can see the speckle data is basically 10 times worse than the AO data in astrometric performance. But you notice that there are these kind of outliers in the data. We didn't know what they were, and so we went back to the original images. So this is an image, and all the orange circles are detections of stars. And you subtract out all the stars you've detected. This is what you get. And it turns out in those epoch, there was this unknown star in the past, which is here. And that was what was biasing those years of astrometry, basically. OK, so now onto the question about reference frames. So this is the big question of how if all stars move, how do we put them in a common coordinate system? And the way we do it is with radio masers. So these stars that are marked in circles are masers, and so they emit really strongly in the radio. And so in the radio, people have measured, actually Mark Reed has measured them with respect to Sagittarius star really precisely. And so this establishes an absolute reference frame, essentially.
These are stars within the Milky Way.
Yeah, this is actually just within about 10 arc seconds from Sagittarius star. So this box is about 10 arc seconds, so about 20-ish is this whole field. So there's about 7 radio masers in the Galactic Center, which are visible in both infrared, this is an infrared picture, and radio.
And their proper motions are negligible or well?
They're well measured in the radio. So there's been a decade or so of radio observations of these stars. And so you can basically propagate the radio position to every single epoch that you've observed in the infrared and then construct your reference system that way. And so that's to answer your question of how do we tie all the images together. And this process is actually fairly complicated because you can see that, so this dash box is one image, basically, one pointing of our imager. To get these radio masers, you need to mosaic. So there's actually several pieces of complications that come with the mosaicing. But in short, we've improved several parts of this. There are new velocities from the radio masers from Mark Reed. And then we built a new point source detection algorithm, and then also high order transformation. So basically, the bottom line is we improved our reference range stability by a factor of 4 for this project. This is basically asking where does the radio think the center of your reference frame is based on the stars. And so these circles are 1, 2, and 3 sigma contours. And so in the past, we got these really big error circles, and now we've reduced them substantially. What does that really mean for orbits? We've been playing around with that. It would be really helpful. The one issue is that Sagittarius star is about 6 to 7 magnitudes fainter than the radio masers, so it's just vastly different in brightness, and also it's also where the stellar density is the highest. So the probability of source bias from just nearby sources is the highest at that location. But we are trying, and it would be really helpful if we can get it to work. So the effect on the orbit of a reference frame drift is shown here, which is this is the 2013 reference frame, and this is the 2017 reference frame. Basically, if you have a reference frame drift, it looks like your orbit doesn't close, right? And so that mimics lots of things, like the precession of the periapse. And so you really need to fix this, right? And so the improvement really helped in that aspect. And in fact, that's the next thing we'd like to do after the redshift test, is to look at the precession of the orbit. And basically, we think we need to hit this referencing stability in order to do that. And we should be able to within a couple of years, I think. OK. Now I've talked about the data. Now we're on to systematics. Basically, astrometry is 99% systematics. So what we want to do here is to think about how our instrument, a way to detect if our instruments have systematics. And it's a big problem for radial velocities, especially because we've used 6 spectrographs over this lifetime of this experiment. And so if the spectrographs are calibrated slightly differently, you would get get differences in the radial velocity, right? And so this is basically color-coded. It's really hard to read this, but nevertheless, this is just to show there's a bunch of different instruments. And so how are we going to do this? The way we're going to do this is to use something called the Bayesian evidence. And basically, it's fairly straightforward. It's just the Bayesian evidence is defined as the probability of giving data given your hypothesis, right? And that's the integral of the likelihood, where theta is the model parameter. And then we're going to use the Bayesian model selection by using the Bayes factor. So basically, you're asking, is hypothesis 1 more probable than hypothesis 2, and take the ratio. And so what we're going to ask is any instrument offset from the other instrument? If you add an offset to one instrument, is that a better hypothesis than if there's no offset to that instrument? And so basically, there's a rough rule of thumb about the size of the Bayes factor correlates with how strong your evidence is. And so when we looked at this,
Is that log base E or 2? Just get the numbers.
log base.
Formerly had before.
Oh, this is E, yeah. Log base E, yeah. Yeah.
Just wanted to connect with the numbers with E.
Right. That is a good point, yeah. So basically, there's one instrument that has a very significant offset according to this Bayesian model selection. And so we looked at why in the original data. And it turns out that instrument had really strong optical fringing, which we didn't recognize in 2002 when the data was taken, there was a bias until we now have much more data to do that. And so we can do the same with the astrometry. Luckily, astrometry has only 2 instruments, so the Speckle instrument and then this new AO instrument. And in that case, there was no significant offset necessary for either components. And the other thing you can do is to look at how the astrometry is correlated with time. And the reason why this is important is because you can think of the Galactic Center as like a sea of stars that you don't see, right? We are only seeing the tip of the iceberg, right? We at the Galactic Center, we're kind of only sensitive to stars above maybe like 3 to 5 solar masses. So there's tons of things below that we can't tell. And so what that can occur is that you can have correlations in astrometry over the scale of several years as stars cross each other, basically, underneath. And so by adding a correlation, a spatial correlation, into your orbit model, you can try to detect that, basically. And that's what it actually shows. So it shows that there's a correlation at a scale of about 30 milliarc seconds or so, which is about half a angular resolution element, which is approximately the level that some of the correlations that exist. OK, I don't have time to talk about all these other ones, but the other things that we looked at is whether, because we're using a Bayesian inference for our orbit model, whether our choice of priors matter. Second is if there's a binary companion to SO2, right? That would definitely mess with the redshift. We are pretty certain there isn't one that's like large, massive enough to affect it. And then we did a reference frame uncertainties. OK, results. So now onward to things. So the way we parameterize the redshift is that we're going to use this parameter to describe the redshift. And this redshift actually consists of 2 components. There's a special relativistic component and a GR component. And we can't really tell between the 2, basically, because they're all folded in together. And so we assume special relativity is correct. And so we're just going to test this general relativistic component. So when we say the redshift constraints, that's what we mean. At the other 2 components, this is the radial velocity offset. This is basically the bulk offset of the whole system. So this is why what you think your 0 point in radial velocity really matters. And then this is from the Contrarian model. And in fact, our model has something like 13 different parameters. Basically, there's black hole parameters like the mass, the distance. And then we also let the position and velocity of the black hole move independently. There are 6 stellar orbital parameters. There's this instrumental offset that we fit for simultaneously. And then there's the correlation length and mix and the coefficient. Okay, and this is the orbit. So now we have these. These are the new data points from 2018 in astrometry, and then over here in radial velocity. So you can see we cover both maximum and minimum. Okay, and then we're going to use a Bayes factor to do a simple thing, which is to test what is the probability that that GR is a better model than a Newtonian model, right? And it's huge. It's ln of 10.7. So that corresponds to like the GR model is 43,000 times more likely than the Newtonian model. Maybe not surprising, but it's still really awesome to see it work around a supermassive black hole. So
This is the first time that's been done for that A star, that the GR model, GR is clearly better than
yeah,
in
yeah.
statistical sense, yes.
Right, right, yeah, yeah. The gravity group also, at VLT also made a similar measurement, yeah. So here is now zoomed in. So remember I was showing the like 200 kilometers per second peak thing. So this is what it is. So this plot's a little complicated, so I'm going to explain a little more. So on the x-axis is time. So we're just focusing on 2017 to 18. And then the y-axis is the RV deviation of the Newtonian model, meaning given the best fit GR model, you subtract out the Newtonian component. What do you have left? And that's what this dotted line is. And the solid line is the Newtonian, obviously. So it's 0 by definition. And then our data is in black. The error bars are about 1 sigma. And then our best fit model, which includes more than these data points, right, is in 1 sigma is this green contour, and then 2 sigma is this gray contour. So if you instead want to look at probability distributions, this is the probability distribution for the redshift parameter. And so it's something like 0.9-ish, and where GR would be 1 in this parameterization. So long story short, GR is still consistent, but we have a significant detection of this redshift. So what does this tell us about gravity around a supermassive black hole? Basically, Einstein is right for now. We'd like to do more tests. But what else? Here's where some of the complications come in, which is that the redshift is strongly correlated with black hole and angular orbital parameters. So if you can push down these black hole and angular parameters, you could get a much better redshift measurement in the future. So these are the joint probability distributions of different model parameters that are the most correlated. So some of these are, I would say, are more obvious than others. So for example, the mass of the black hole is really correlated with the redshift, right? Obviously, it should scale with mass. Same as with distance, because distance and mass are correlated as well. But what, and this is why VZ naught is important. It's that the absolute velocity of the whole system is actually really correlated with redshift as well. So being able to fix the absolute scale is important. And then these angular parameters I didn't quite expect, which is like the angles of the orbit actually does correlate a lot. And I think that has to do with basically if your angles change, you're pushing closest approach further or closer to the black hole. Okay, and then the other things that are interesting to folks, I think, are the mass of the black hole itself and then the distance to the galactic center. So both of these are now, the uncertainties have gone down quite a bit. So the black hole is about 3.95 solar masses. The distance to the galactic center is 7.93, 7,934 parsecs. Okay. The other thing you can try to test is look for the existence of extended mass around the black hole, because this region probably accumulated a ton of neutron stars, stellar mass black holes, et cetera. Right now, we are, sorry.
Results consistent with the gravity groups within the same layers?
They are not. They are almost about 3 sigma different. The errors are very, very, very tiny now. So one of the challenges, I think, in the coming several years is to figure out how the two, because the heart of it is the details, right? Like how the astrometry was constructed, how the reference was constructed, things like that. So there's lots of areas where systematics can creep in.
You haven't done a little bit larger than those two.
Yeah, so the VLT group got numbers that are slightly bigger than these. So I think they are at 4.1 in black hole mass, and then a little over 8 kiloparsecs, 8.1 or something. But these two parameters are completely correlated. So if one goes up, the other will go up as well. Yeah. OK, so this is the extended mass distribution. So at 1 sigma confidence interval, we can say that there's less than about 5,000 solar masses inside the orbit of SO2. So the next thing we'd like to do is the precession of the orbit of SO2. So in precession, this is Mercury around the Sun. Basically, it just means it doesn't start where it ends off, and that has to do with the way the orbit moves through space-time. OK, one of the really important things is that we probably can't do this with SO2 alone. And the reason is because extended mass causes exactly the opposite sense in the precession. So basically, I think GR causes a prograde prograde, and then the other one goes the other way, the retrograde. I always get the two confused. So, but anyway, it's they go in opposite sense. And so if you basically say, OK, let's make an experiment where we have astrometric error of 100 microarc seconds when we have 20 microarc seconds. How well can you do in measuring the precession of the periapse? So this is the signal to noise of the periapse signal now of the rotation. If you fit only GR without extended mass, you basically, with SO2, you basically get this rapid improvement in your signal. But if you just add this one extra parameter, which is the extended mass, into it, suddenly you kind of plateau. And no matter how much more data you take, it's actually really, really difficult to be able to decouple the signal. So what's the solution? The solution is to use other stars, right? There's a ton of other stars in the region, and they have different orbital planes, and that's actually what helps a lot. And they have also different semi-major axes. And so this is basically this plot. It's the same as the other plot, except that now we're adding one other star. So basically, this is with SO2 alone, and then this blue one is SO2 plus SO1, and the orange is SO2 plus SO5. So these two are the most promising stars, probably, to add into the analysis. You could also imagine adding every star in as well. OK, the other thing is that even like minor confusion events can really, really bias this, because you're looking at a rotation of the orbit. So if we just model a little bit of confusion in the orbit, meaning that the stellar positions are just moved slightly because of the underlying sea of stars, you can get basically, so GR once again is 1. So you have perfect measurements with no confusion. You're here. But with just a little bit of confusion, you can get like an 8 sigma deviation from GR very easily, actually. And so systematics will be the name of the game. As a TMT institution, I can't help but show this video, which is what the Galactic Center will look like with the 30-meter telescope. And this will be basically key to a lot of these tests in the future, right? We're talking about looking at SO2 for 16 years before we can make this test. This is today's adaptive optics. This is the adaptive optics system we're building right now at Keck. And then this is with the 30-meter telescope. So with the 30-meter telescope, we expect to be able to see stars with just 3-year orbital periods. So like a grad student lifetime, you could like do this whole experiment. Yeah. So we wrote a large number of papers in support of this work, and they're here. I just highlight like some of the ones from grad students. So Devin wrote this about the binary stars. Kelly wrote this about the improving orbital estimates. Xiao wrote this paper about improving the astrometry. And then we have one on the reference frame. This is our adaptive scheduling tool. And then this last one is our relativistic measurement. OK, so I just for this part of the talk, let's leave you with two things, which is we're entering an era of GR tests, the Galactic Center. Finally, a lot of people have predicted this in the past, and we really see this going forward now. And then understanding systematics will be even more important in the future. Before I move on, is there any questions about that part? Yeah.
Were there any theories that predicted deviation or deviation was possible at this scale for potential?
We didn't expect necessarily to see a deviation from any predicted theory at the moment. Yeah, so it's not precise enough yet.
So you haven't added constraints in any of the PPM?
I think it depends on the, well, we've parameterized the this redshift, so you can there's a related PPM parameter like alpha basically, which is related to this I've forgotten what the name of that Greek character is, but whatever we call the epsilon. Yeah, there's an epsilon. The epsilon parameter it's related to like the alpha parameter in PPM. So.
Is your constraint tight to pre-existing PPM constraints?
It's not tighter than solar system constraints. Solar system constraints are several orders of magnitude better, but it's kind of the only one we have around a supermassive black hole. Yeah. Yes.
You measure some limit to the extended mass distribution, the extended mass within the very small particles. Does this limit give any significant information about the dark matter density there?
By dark matter, do you mean actual dark matter, or no? So that mass value is still too high to and the dark matter density profile is super uncertain, right, at that scale.
I'm interested if that can help understand
Right.
what's happening right here.
Right. I think in the future we could. Another thing in the future that could help is actually whether you can detect dark stars. I have a whole other thing about this, which is like, those may actually be the most promising. So because TMT should be able to see those. Yeah. Yes.
You talked about astrometry and spectroscopy, not photometry, which is apart from anyway. So the radial velocity signal is about percent the speed of light. Can you detect the brightening SO2 comparison due to its motion?
So the reason we can't because our photometric errors are at best about 3%. So yeah, it's a good thought, but maybe with a much larger telescope or more sensitive. Okay, so I'm just going to move quickly through this because I only have a little over 10 minutes. So Sagittarius star itself, like I said, it's an emissive source. So in the infrared, it looks kind of like this. This is a color image of a 3-color image of 1.6 microns, 2.2 microns, and 3.8 microns. So the 3.8 microns is L-band, and so you can see it's very red, and it sort of flickers in the middle right here.
What time scale are we looking at here?
So the whole movie is about 3 hours. Yeah. And first, before I talk about the variability, I'll just talk a little bit about what makes the emission of Sagittarius star. And this is a theoretical spectral energy distribution in the quiescent state of Sagittarius star. And so most of the radiation from Sagittarius star comes out at radio wavelengths. Its peak is in the submillimeter, and then you see some infrared emission from a combination of synchrotron and non-thermal electrons, synchrotron from thermal electrons and from non-thermal electrons, and then in the X-ray you see a combination of inverse Compton and Bremsstrahlung. But what I'm interested in is what's going on in infrared. So the infrared can vary quite a bit, and the first detection of Sagittarius star that was reported was in this paper by Genzel in 2003, where they showed that over these 1 to 2 hour, 2 to 3 hour timescales, Sagittarius star varies quite a bit, right? So in purple is Sagittarius star, and then in red is a star. So the question we have is, what's the nature of this variability? In particular, in this case, they they reported maybe there's a sign of periodic behavior to the infrared emission. Okay, so this is some other examples of light curves in Sagittarius star. Now this is with Keck data, and you can see that most of the time the variability, so this flux is in 2 micron flux, and this is observed flux, so I haven't corrected for the extinction to the Galactic Center. So it kind of wobbles between 0.1-ish to 1 millijanskis over these different nights. And if you were to look at the variability characteristics, so make a power spectrum of the nights, you see this. So this plot is power, and then this is frequency. This is a periodogram. It's not quite a Fourier transform. You can think of it like a Fourier transform. So basically, it mostly follows a power law, and which means that this is a red noise spectrum. So basically, when Sagittarius star is it's bright, it's more variable than when it's faint. And so its variability is correlated with its brightness. Okay. And also, there doesn't seem to be any significant periodic signal in this data. This big spike here is actually our dithering time scale, about 3 minutes. And so that's why in order to do a lot of Sagittarius star work, you need to basically simulate your data through these variability processes. And the dotted blue line is our simulation. And so you see our simulation replicates this.
Assuming a pure power law.
Exactly, yeah. So basically these are assuming these different simulations of power law. Okay, so it's basically very close to a power law of 2, essentially, Sagittarius star. So now, okay, fast forward over 10 years. Oh, it's something like 20-ish minutes. So I wish I made this in pure. It's like over here somewhere, I think. No. Yeah, so the reason, yeah, I can get to it much more, but let's move on for lack of time. So let's fast forward about 10 years. Now we have a lot of data on Sagittarius star, right? We have over 13,000 data points from 133 nights from DLT and Keck. So this data was published in Witzel et al. In 2018. This is the histogram of the flux distribution of Sagittarius star. So you can see it sort of matches what we were seeing before. It goes up to about, actually, there's some points all the way up to here, but there's a very long tail. It's like a log normal distribution. Okay, and with a lot of the AO data, we were limited to about 3-hour chunks. That's just how much time the Sagittarius star is above the sky, basically. That's observable from Mauna Kea. And so to look at longer time scales, what you need to do is go to space, essentially. And so this is work using Spitzer Space Telescope. And so you can get whole, like 24-hour chunks of Sagittarius star measurements. And this is 8 light curves, 24 hours long. And with Spitzer, of course, you're going to longer wavelengths to do that. Okay. So what happens if you put together all this data and ask what is the power spectrum of the source? And it turns out that basically in this parameter space you can have a break frequency in the power spectrum and then the slope of the power spectrum. So in the 2018 data, basically we've now isolated the slope and power spectrum to pretty precise values. There were some indications already in 2009 that the power spectrum of Sagittarius star must break at about the 240-minute time scale. And this is kind of what it looks like in the PSD space now with all the data together. And so here's the break frequency. And then it's it's basically follows a power law of 2 down to this white noise floor. So this is when the noise sets in and you can't measure intrinsic power anymore. And I was talking about the speckle analysis. So we went back. Remember, the first AO detection was in 2003, but the first speckle data was all the way in 1995. And so if you want to look at Sagittarius star over really long time scales, you should look in the speckle data. And so in fact, one of our grad students, Joel Chen, she went back to the Speckle data and was able to detect Sagittarius star in actually many epochs in the Speckle era. And so she was able to extend the time baseline by another almost 10 years. And so here's her light curve of Sagittarius star as a function of time. So even in the past, it's very consistent with the current brightness of Sagittarius star. So basically, this was the timescale probe in Witzel et al. In 2018, and this is a timescale that was in Chen et al. Probing this timescale. It's a little complicated to do this work because it's always variable, right? So you always need to work backwards via Monte Carlo simulations to figure out if your data is consistent. So basically, from the given our model, our expectation is this should be the flux distribution, and this is the range of fluxes we detect for Speckle. And so it seems pretty consistent. And so in 2018, we wrote this paper, and near the end, we said, it is surprising how steady the statistical, spectral, and polarimetric parameters describing the variability of Sagittarius star has been since the beginning of AO observations. Okay, so this is like the most comprehensive paper because it had all the data, right? And then, like this happened in May of this year. So in the middle, I guess I don't even have to point to it. It's that's Sagittarius star. It became super bright. This is SO2, which is 14th magnitudes. And Sagittarius star got as bright as, it was 12.7th magnitude in the beginning of the night, which means it was probably even brighter in the earlier before we started observing. And so this was very weird. And here's a diagram of it. So this is the star here. If Sagittarius star was always this bright, we would definitely have been able to do it in this Maser reference frame thing. We would have taken a spectrum of Sagittarius star. It would have been discovered like with seeing limited observations. Anyway, so it's incredibly bright. So you can see that it dropped by a factor of about 75 in 2 hours in brightness. And then over here, it dropped by a factor of 2 in brightness in just 7 minutes. So whatever the emitting region of this flux is very small. This corresponds to about 3 short shell radii at the distance to the Galactic Center.
There is comparable to the long-term average over many years?
Over here.
Yeah.
Yeah.
Going back to
Well, I mean, it's always variable, but yeah. Yeah. So we normally see like peaks kind of every 3-4 hours. That's kind of the break time scale, right? But we've never seen ones that are this bright. And in fact, out of 3 or 4 of the 4 nights that we published, Sagittarius star was pretty bright. So this was all the data that I had when I published this paper. So basically, this is the light curves, and then I've drawn in dashes basically the historical flux distribution of Sagittarius star. So basically, anything above this is above 95% of all observed historical flux. This is above 99.7%, and this is 100%. So basically, this is the brightest night. It got about twice as bright as the brightest previous historical flux. But all of these 3 nights reached at least 95%, and this one went above 99.7%. So you can look at it a different way, which is to compare the flux distribution of that we saw this year with the historical flux distribution I showed you previously. So in gray, at the top is the historical flux distribution, and then scaled the distribution this year in black. And then on the bottom is just zoomed in. So basically, we're seeing this really long tail here. And we can ask probabilistically how often would you see this, given our model with the historical flux data. So that's a caveat, right? So they're probably observing any night as bright as the May 13th night, given all previous Keck nights. So to phrase it, we did this in a frequentist way. So basically, if you observed all the Keck data 10,000 times, how many of those 10,000 times would you see something this bright? And it's something like 0.3%. And then you can ask the question is, what's the probability of seeing the brightest flux from all 4 nights? And that probability is something like less than 0.05%. But at these very small probabilities, then it just becomes errors on the statistical on their model, right? So it's not that informative. It's just informative that it's very slow probability given the model. OK, so what's going on? I don't know. But there are two interesting models that I've been thinking about. One is that, well, SO2 just went through closest approach. So could its closest approach affect the usual accretion flow that's onto Sagittarius star and change it somehow such that now more gas or a higher rate of accretion is happening? Two is that there was this object that went through closest approach in 2014 called G2. Now, we still don't know exactly what G2 is, but whatever it is, it has a lot of gas, and it's spatially resolved, so it's actually quite large in physical size. And when it went through closest approach, it got bigger and then got smaller as it went out of closest approach. So that probably means that some of the gas was expelled from the source. And the expectation in 2014 when it went through closest approach was that maybe it would light up the Sagittarius star, but we saw nothing in 2014. But that might not be surprising because it takes a while for the gas to lose its angular momentum to fall into Sagittarius star. And so maybe we're just starting to see signs of this happening. And so I'll just leave you with 4 questions I have about this event, which is what is the time evolution of Sagittarius star's behavior this year? We've been tracking Sagittarius star after this paper, and then other groups have also been tracking it in the X-ray and radio as well. And then do we need a new statistical model of Sagittarius star, right? Because we've just shown these very large outliers. Is this a precursor to a larger event? This would be exciting to see. And then how do we narrow down the range of physical mechanisms that could cause this? OK, I am out of time, but if there's any questions, you know.